Ladies and gentlemen, it's good to be back. It's been nearly a month since I made a video for you, and I know that you are desperately missing those new videos. So hopefully you'll go through this one and really enjoy the calculus. I know this is a Christmas comic, but I do think it was certainly a good commentary on Americans' willingness to sacrifice, or lack thereof, if you will, as we are a very selfish society. But you know that political statement aside, let's get started with the calculus. Today we start Chapter 8. Chapter 8 is all about sequences. And today, about half the lesson, we're just going to review probably what you already know about sequences. And then we'll actually talk about where some of the calculus comes into play. We'll talk about defining a sequence. We'll talk about the differences between arithmetic and geometric sequences. I'll show you how to use your calculator to graph a sequence. And then we'll get to the calculus and we'll talk about limit of a sequence. So what is a sequence? A sequence is a list of numbers written in an explicit order. For example, we might have something that looks like this. A sub n equals a1, 2, 3, 4 all the way to n. This is a sequence. You know what a sequence is. It's just a list of numbers that do have a specific order. Many sequences are made null and void if you change their order. It has to be in a certain order. Now, in this class, we're going to study two kinds of sequences. We are going to study finite sequences, those, of course, being sequences that have an end. And we're going to look at some infinite sequences, those that will go on to infinity. Alright, let's talk first of all about defining a sequence explicitly. Now, you're going to see two terms that come up with sequences. One is explicitly and one is recursively. Explicitly is simply an equation. So if you want a certain number of terms, say you want the 12th term, you just plug 12 into the equation. A recursive sequence, you're going to find out in a moment, you can't do that because a recursive sequence requires you to know previous answers before you can find a certain answer. But we'll get to that in a moment. So we need to find the first 6 terms and the 100th term of this sequence. Well, the first term would be just plug in 1 for n. So if I plug in 1 for n, plug it in there, and I plug it in here, and simplify, you get negative 1/2. The second term you would find by plugging in 2 for n. So plug that in and simplify, you get 1/5. The third term, plug in 3, negative 1/10. The fourth term, you're going to plug in 4, and you get 1/17. If I can move the screen down just a little bit. Then we're going to plug in the fifth term, plug in 5 for the fifth term, negative 1/26, and the sixth term, 1/37, and then we plug in the 100th term, and we have this number. Not difficult at all. It's just a matter of plugging in the numbers and simplifying. Much easier to deal with things explicitly than it is to do so recursively. And speaking of which, here's our recursive function. Now, a recursive function does not have a single equation. A recursive function will have, first of all, a starting value. It will also have a rule that says what we need to do to get to the next term. In this case, we're going to take the previous term, add 2. And then it lists the domain. I'm not overly concerned with the domain part here. Some books, in fact, won't even list the domain. So if you want to list it, that's fine. If you don't want to list it, I don't care. Just make sure if it comes to the AP exam, if it asks for you to list it, you do list. Alright, it wants us to come up with the first 4 terms and the 8th term for this particular problem. Well, we know what the first term is already. The first term is 4. That was already given to us. Now, to get the next term, we'll take the 4, which we had previously, and we'll add 2. We got 6. To get the term after that, we're going to take that 6 that we just got, add 2 again, and we have 8. Again, to get the next term, you just add the previous term in 2. So here's the previous term, which is B3. To get B4, add 2 again, and you get 10. Now, how are we going to get the 8th term? Well, if we consider 5, 6, and 7, we add 2 each time. 10 and 2 is 12. 12 and 2 is 14. 14 and 2 is 16. So if we add 2 one more time, for the 8th term, we get 18. That is a recursive function. You can see where the drawbacks would be. If you were wanting the 100th or 200th term, obviously you don't have to sit and do that every single time. but that's how a recursive function works. Alright, arithmetic sequences. An arithmetic sequence is one. It says it can be written in this form, a plus d, a plus 2d, and so on. But quite frankly, simply put, an arithmetic sequence is one that simply adds a number each time. Now, if you think about a sequence like the odd numbers, 1, 3, 5, 7, 9, 11, and so on, you're adding 2 each time. There's a common difference, see the word common difference of 2. That would be an arithmetic sequence. Now, ladies and gentlemen, I want you to take note of this right here. That's a very important formula. A sub n equals a sub 1 plus n minus 1d. If you have an arithmetic sequence and you need a certain number of terms, the 80th term, the 1000th term, and so on, rather than adding the same number over and over and over again, you can go straight to this, and this suddenly takes a recursive function and it makes it explicit, and it makes it much easier to deal with. Alright, let me erase this here. This is an arithmetic sequence. You add the same number, or subtract the same number, if you will, every time. Let me move our screen back up here for just a moment. There we go. Alright, our instructions say, find the common difference. You see it just came up when I was trying to move the screen. The 9th term, a recursive rule, and the explicit rule for this sequence. Well, first of all, I see very clearly that the common difference is 3. I see that I'm adding 3. Negative 5 and 3 is negative 2. Negative 2 and 3 is 1. And so I'm adding 3 every time, so the common difference is 3. How am I going to find the 9th term? Well, I can just keep adding 3. There's 1, 2, 3, 4, 5. So the 6th term would be 10 if you add. The next term would be 13, and then 16, and then all the way down to 19. But again, that was the 9th term. What if I wanted the 999th term? That's not very efficient. So let's think of some rules. First of all, let's think about the recursive rule. Now, the recursive rule requires you to, 1, come up with the initial term. The initial term is negative 5. And 2, tell what you're doing each time to get the next term. In this case, add 3. So my recursive function is going to look like, hold on, I got to back up a little bit. Is going to look like this. Now, I didn't, although I should have included this. You do need to include this right here. You do need to include your statement about the initial term. So I start out at negative 5, and then from there I add 3 each and every time. This would be my recursive rule. Alright? Now, how do I come up with the explicit rule? Remember the formula that I showed you a moment ago? A sub n equals a sub 1 plus n minus 1d? That's what this is. This is what we use to come up with the recursive rule. Now, an explicit rule. You could leave it like this, but that's really not simplified. So I'll distribute my 3, and then I will combine my like terms, and my explicit rule is a sub n equals 3n minus 8. Again, this is what is very useful. So if I wanted the 1000th term, I would just plug in 1000 for n and simplify. Then I don't have to keep adding 3 over and over and over again. A geometric sequence is somewhat similar to an arithmetic sequence, but this time, instead of adding the same number every time or subtracting, you're going to be multiplying or dividing. Technically, you're multiplying every time. It's just by a number by a fraction. The number that you multiply by every time is called the common ratio. Again, if I may bring your attention to a formula right here, a sub n equals a sub 1 times r to the n minus 1. That is our formula that we use to come up with the explicit formulas for a geometric sequence. Alright, so same thing here for a geometric sequence that we did on the last one for the arithmetic sequence. I've got my list of numbers here. I want to come up with some various things. First of all, I want the common ratio. Well, what am I multiplying by each time? Well, first of all, I see it's alternating negative positive. The only way that's going to happen is if I'm multiplying by a negative. But negative what? Well, you see it's also doubling, so each time I'm multiplying by negative 2. Now, I want the 10th term, so there's 1, 2, 3, 4, 5 terms already. Term 6 would be negative 32. Term 7 would be positive 64. 8 would be negative 128. 9, 256, and then 10 would be negative 512. Again, just reasoning through multiplying in my head. A recursive rule. What's my first term? My first term is -1, so I would write a sub 1 equals 1. And what am I doing each time? I'm taking that previous term and multiplying it by -2. So again, don't forget to also write your beginning amount. You do have to include that in your answer. AP people will take off if you don't do that. Now, what about an explicit rule? Well, again, I go back to this formula right here. A sub n equals a sub 1 times r to the n minus 1. Well, the starting term is 1. The rate is -2. So I'll take that. Simplify it. Really, there's nothing to do to simplify because the 1 does nothing. And so I just drop the 1, and there's my explicit rule. So if I want the 1,000th term, I'll plug in 1,000 in for n. Alright, now let's actually make a sequence. I tell you that the second and fifth terms of a geometric sequence are 6 and -48 respectively. Given that, let's find the first term, the common ratio, and an explicit term for the nth term. Alright, to do this, it's actually not too hard. I'm going to start with this statement right here. I know that the second term is 6. So if I take my a sub n equals a sub 1 r to the n minus 1, if I plug 2 in for n, I get 6 out for an answer. Simplify that down. 2 minus 1 is 1, so I have r to the first. And I can solve for a sub 1. That equals 6 over r, and you'll see why in a moment I'm doing that. Now I also know that the fifth term is -48. Now, sorry, we had a little glitch in the program there. Here's what we have. Now, I'm going to simplify this, ladies and gentlemen. 5 minus 1 is 4. And remember, I solved for a sub 1 a moment ago. A sub 1 is 6 over r. So we now have this. And now it just goes to solve for r. So I simplify that r, and r to the fourth is r cubed. Divide by 6, which is -8. Take the cube root. Cube root of -8 is -2. So now if r is -2, I can plug that in up here. 6 divided by -2 is -3. And now I can plug those in, and this is my explicit rule. A sub n equals a sub 1, -3, times r, -2 to the n minus 1. Sorry about the little glitch there in the program. Now, the next thing that we're going to do is we're going to sketch a graph. Now, I've got the graph on here, and I'll show you what it looks like. It looks like this. But I want to show you how you graph this on your graphing calculator. And I know this is going to extend our video just a little bit, but I think it's worth it. So what I'm going to do is I'm going to hit escape here on the PowerPoints, and I'm going to pull up the graphing calculator. Let's see. No, I don't want to add the drawing. That's fine. I want to pull up the calculator right here on my graph. And just to show you, you may not have a graphing calculator with you right now. That's okay. You can look at it tomorrow. Now our function was to be graphed in, if you look here, parametric mode. Now that's not sequential. We do have sequential graphing, but this one is in parametric mode. Because you can do parametric graphing for a sequence. So here's what I'm going to do. I'm going to go back here, and I'm going to go mode on my calculator. Menu on my calculator. And I'm going to go to the graph entry, although it may say graph type on yours. Remember, I've got a CAS version here. And I'm going to go to parametric. Now for the X part, I'm just going to put T. And for the Y part, well, if I can move down there, for the Y part I'm going to put the equation, which is -1 to the n, or to the t in this case, -1 to the t, and then t minus 1 over n. So give me a second to do that. So we've got... Alright, ladies and gentlemen, sorry about that. I had a bit of an interruption. I want you to see what I typed in here under parametrics. For the X, I did T. For the Y, I did -1T times T minus 1 all over T. And I did change down here. I changed the T to go from 1 to 10. If you use 0, it won't work because you see the 0 would cause a domain problem here. And I changed it to 10. And you do need to change it to T-step. I changed the T-step to 1. Now, if you look at what we have here, this is not exactly a sequence, but it shows what's happening. It's just it connected all the dots. So you see that the sequence is fluctuating back and forth, back and forth, back and forth. See that we're at the end of the first video, so I'm going to go ahead and save this one. We'll be back in a moment for the next one.